it's that you could all like it probably would be good because it does say determine the behavior of the force. So you might be better off finding the magnitude of that, so you might be better finding the hypotenuse of fx and fy. It's fun getting it, guessing it. You do get over it, so I would encourage you to guess.
So can I see the one above?
Thank you. 1G. No, 1G. G for gauge. So key thing with any other questions with that problem? All fairly easy. Okay. Pretty straightforward. The key things here for this one is that it's a combination of a fluid flow problem and a structural problem, and you can tie those together with the these equations here. The sum of forces is equal to the rate of change of momentum. So anytime you see a problem where it's asking, where you have like a fluid flowing out or fluid flowing in to a system, and you're looking to calculate the forces, you should think, okay, sum of forces in these situations relates to the rate of change of momentum. And we can tell from this, because it's a rate of change of momentum problem, and we have a steady state problem, therefore there's no rate of change of the momentum inside of the volume, so we can get rid of that one. That leaves us with just these simple relationships. And if we can get to there, the rest of it is fairly straightforward. The rest of the process is, simply just listing out things we need to find out. There is a long list. You need to work your way through that and work out how to figure all those things out. But if we can get to that list, the rest of the problem sort of, carries itself forward. Really where the engineering is, the engineering understanding is being able to understand that, okay, we're trying to find the forces, this is a good model for what we're trying to do, and these are the equations we're going to use. That's where the sort of engineering understanding can be shown. Pardon? You could have any shape you want in here. You can go up and down, whatever. So long as this and this are in the same position, the same orientations, and you have the same conditions of flow rate, it's just your control volume will just go to match this. Keep in mind, when we went and used that Bernoulli's equation, I guess that was the other tricky thing. Because we didn't have these pressures, we need to use in the example we did yesterday, we had the pressures, but not the velocities. So we used Bernoulli's to find that out. Today we had the velocities, but we didn't have the pressures. The one thing is, when we use that Bernoulli's equation, we didn't have any friction losses in our system. We sort of ignored those out. If you had more of a a long curvy thing, then you might have significant losses in that. You might need to incorporate that, but that's sort of discussed this one. But if no matter what the shape is, it can go over here, and remember, so long as these exits. Any other questions about that? We have done this with linear these equations here, they are like translational. So we're looking at the linear momentum. So momentum in the x direction, momentum in the y direction, momentum in the z direction. You can also do these equations and look at the rotational momentum, where the rotational momentum h is related to the linear momentum times by, or not times by, but cross product with a radius. So, you know, if I have momentum, you know, if I take a point and I have the momentum coming in, that has to be, like the rate of change of that momentum, that rotational momentum, is equal to the sum of moments on the system. The equations come out all the same. They're just a little bit more tricky in that you now have, like you end up with the same thing here where you have the sum of moments for like a fixed control volume. You have a control volume term, and then you have a control surface term of momentum flowing in and out. When you, this one's a little bit more tricky in that, how am I going to say this? Imagine if you had a pipe, just a straight pipe, and you had fluid all flowing at the same velocity, you sort of have to assume that all that fluid is at the same radius, because really, like, if I'm taking the momentum at this point up here, they all have different radiuses, and so you'd all end up with different sort of rotational momentums. So you have to assume that the pipe is relatively narrow. In order to do this, you can do it with like an integral form, but it gets complicated. So with this, you're sort of assuming that, you know, if you just take the center line of the pipe, you assume that the pipe is relatively small. But you get the same thing. You're looking at, you know, the mass flow in a certain direction across that. Yeah. So relatively like similar sorts of things. It's just a little bit more complicated that you need to think about in terms of the radius. I would like to do this example, but I don't think we have time to take several more examples of what we did. So that leaves us with that. Is there any questions about any of that stuff? Okay, dimensional analysis. So dimensional analysis is where we're talking about pi groups using the Buckingham method. Also known as dimensional similarity. Very widely used, more so like not just, it's used in fluid dynamics, it's used in fluid dynamics, but it's used across a whole bunch of industries. My research group back at RMIT, we recently did one. We did a dimensional analysis. First time it's been done, we did it for vehicles, which means that we come up with some Buckingham groups and some pi groups that allowed us to scale up and down cars, rather scale down cars, so that rather than we were wanting to do testing of a series of vehicles operating at very high speeds, which is going to be very, very expensive for us to complete that testing. So instead, rather than doing full-scale testing, we came up with Buckingham groups, which means we can sort of use 1 to 24 scale vehicles, so about that big. We have to put weights on and things like that to sort of scale them according to the groups, but it means we can actually carry out doing the test. And the basis of it is dimensional similarity. So there are a whole bunch of 7 primary dimensions you can work with. Mass, length, time, temperature, current, amount of light matter, amount of stuff. You can derive any other unit knowing these. We typically don't deal with one or two. Sometimes, very rarely do we deal with current. So typically for us as mechanical engineers, we're dealing with these top 4: mass, length, time, maybe temperature. And primarily we're dealing with the top 3 really. Most of the systems we're working with, you can just quite like that. I want to go through all this, but I think probably best to go through some examples to make sure we can understand it that way. What the process does, like the end outcome of the process is that we end up with a set of dimensionless parameters which will suggest that the systems are dynamically similar. Which means that the dynamics which are occurring on these different scales are operating in the same sort of modes. This is, it can be very, very useful, but you do need to pay attention to the details and making sure you're capturing all the correct dynamics. So we'll talk about that actually through the examples, but yeah, you do need to make sure you're capturing the right dynamics when you do these. You've gone through all this. I don't want to spend time going through each individual step. We'll do that in the examples, and we'll start with this one. Right. So we have here a submarine, as we always do. They have a full-scale submarine they want to build. It's 4.85 meters long, and they want to. When it travels, it's going at 40 meters a second. The water has a density of this and the viscosity of that. We want to build a 1/5 scale model, so we want to reduce the length by 5 meters to be able to fit it in the wind tunnel. And the question is, what airspeed do we need to run it at to get dimensional similarity? Make sure we get realistic results. Right. So start copying down that. Good. I'll be back in a second.